The ground beneath Yellowstone National Park has risen more than 70 centimeters since systematic monitoring began. Not over 1,000 years. Not over a century. Since the sensors were installed, right now, GPS stations positioned across the park are transmitting daily measurements, showing that the surface is moving upward, laterally, in patterns that geologists track with the same attention a cardiologist gives to an irregular heartbeat. 4 million people visit Yellowstone every year. They photograph the geysers, they watch the bison. Almost none of them know they are standing on the largest active volcanic system in North America. A system that has already destroyed this continent 3 times. Hit that subscribe button. This goes deeper than any documentary you've seen. Don't gamble on finding this again. The textbooks describe Yellowstone as a geothermal hotspot. That description is technically accurate and almost completely misleading. A hotspot implies something contained, something predictable, something that behaves within the parameters of ordinary geological risk. What the data actually shows is a magma chamber covering an area larger than the state of Rhode Island, sitting beneath one of the most iconic landscapes in American history, connected to a volcanic history so extreme that geologists needed a new category to describe it. In this investigation, we will move through 7 stages, from the warning signals already recorded, to the mechanics of an eruption that has no modern equivalent, to what the geological record tells us happens to the planet in the years that follow. What you will understand by the end of this video is not a theory. It is the documented history of what this system has already done, and the precise scientific reason why it will do it again. Yellowstone is not a volcano. It is a caldera, a collapsed magma chamber so large that it was not identified as a volcanic structure until 1960, because no one was looking at a scale that size. That distinction is not semantic. A conventional volcano is a mountain that ejects material from a central vent. A caldera is what remains after a volcanic system so powerful that it collapses inward on itself. Following an eruption, the rim of the Yellowstone caldera stretches 55 miles from end to end. The structure is visible from space, but nearly invisible at ground level, because you cannot see the edge of something when you are standing inside it. The park's most famous geological features, the Grand Prismatic Spring, Old Faithful, the Norris Geyser Basin, are all expressions of the same underground heat source, separated by miles, all drawing from the same magma system beneath. Stop and translate that into physical reality. In the summer of 2003, Steamboat Geyser, which had been essentially dormant for nearly 50 years, erupted without warning. Thermal ground temperatures in the Norris Geyser Basin rose so dramatically that the Park Service closed established hiking trails because the wooden boardwalks were beginning to melt. Rangers observed bison moving away from thermal zones they had occupied for decades. The official public statement from the USGS described the activity as within the range of normal geological variation. The internal documentation from that same period, released years later under Freedom of Information requests, described ground deformation rates accelerating beyond the recorded baseline. The warning signs of 2003 were real, but they were also the smallest signal on record compared to what the geology beneath Yellowstone shows has happened before. To understand why, you need to understand what a VEI-8 eruption actually is, and why the term supervolcano was not invented for dramatic effect. It was invented because the existing scale of volcanic measurements simply ran out of numbers. The volcanic explosivity index runs from 0 to 8. Every increment represents roughly 10 times the explosive force of the previous level. The 1980 eruption of Mount St. Helens, which killed 57 people, flattened 230 square miles of forest, and sent ash across 11 states, was a VEI-5. The 1815 eruption of Mount Tambora in Indonesia, which caused the year without a summer and contributed to crop failures across Europe and North America, was a VEI. A VEI-8 event is 10 times more powerful than Tambora. Yellowstone's last 3 eruptions were all VEI8. The discovery of what lies beneath the park and how that discovery was made changes the question entirely. In 1960, a geologist named Bob Christensen was working for the United States Geological Survey, conducting aerial mapping of Yellowstone National Park. His assignment was routine. What he found was not. Looking at photographs taken at high altitude, Christensen noticed a series of topographic features that did not fit any conventional geological interpretation. The rim of what would eventually be identified as the Yellowstone caldera was so vast that previous research had simply never looked at a frame wide enough to see it. Individual features had been catalogued for decades. The overall structure had been invisible. When Christensen's findings were submitted for publication, the initial response within the USGS was cautious. The implication of a caldera of that size, sitting beneath an active national park, in a region with millions of annual visitors, required careful handling. The finding was real. The geological evidence was unambiguous, but the question of how to communicate the discovery to the public, and what obligations that discovery created, was not purely scientific. The caldera Christensen identified is 55 miles long and 45 miles wide. Placed over Washington, D.C., it would erase everything within the Beltway and extend roughly 20 miles beyond it in every direction. That is not the impact zone of an eruption. That is the size of the volcanic structure itself. Consider what that means. The magma chamber beneath Yellowstone has been imaged using seismic tomography, essentially a sonar system that uses earthquake waves to map underground structures. What those images show is a reservoir of partially molten rock, extending from approximately 5 miles below the surface to roughly 10 miles deep, containing an estimated 15 to 30% molten material by volume. Directly beneath that, a second, deeper reservoir was identified in 2015, containing roughly 4.4 times the volume of the upper chamber. The two reservoirs together hold enough magma to fill the Grand Canyon approximately 11 times. The system is not static. GPS measurements installed across the park show that the ground at Yellowstone rises and falls in measurable cycles. Between 2004 and 2010, the caldera floor rose at approximately 7 centimeters per year, the fastest rate recorded since systematic monitoring began. It then slowed, stabilized, and in some areas began to subside. Geologists describe this movement as breathing the magma system expanding and contracting as pressure builds and releases through hydrothermal activity. Archaeological evidence from indigenous sites around the park perimeter shows this breathing has been occurring for centuries. There are ancient campsites along what was once the shoreline of Yellowstone Lake now, sitting meters above the current waterline, pushed upward by caldera inflation that happened long before any instrument was in place to record it. The ground was moving before anyone was watching. The natural question is whether this breathing represents normal variation or a precursor to something larger. The honest answer from the geological community is that the distinction is not as clean as public statements suggest. What is not uncertain is the historical record. Yellowstone has erupted at VEI8 scale 3 times. 2.1 million years ago, 1.3 million years ago, and 640,000 years ago. The intervals between those events are roughly 700,000 years and 660,000 years, respectively. The most recent was 640,000 years ago. No geologist will tell you that number is a countdown. But what comes next, the actual mechanics of a VEI8 eruption, makes even this context feel like the quiet before something else entirely. The reason Yellowstone does not erupt the way Kilauea erupts slowly, visibly, with lava flowing in channels that cameras can follow, comes down to a single property of its magma: silica content. The magma beneath Yellowstone is rhyolitic, meaning it carries an exceptionally high concentration of silicon dioxide. High silica content makes magma viscous, not fluid and flowing, but thick, resistant, capable of holding dissolved gases under pressure the way a sealed bottle holds carbonation. When the pressure containment fails, the release is not a flow. It is an explosion. The comparison to nuclear detonations is not rhetorical. The 1980 Mount St. Helens eruption released energy equivalent to roughly 1,600 Hiroshima-scale nuclear bombs. Yellowstone eruption is estimated at between 1,000 and 10,000 times the energy of St. Helens. The comparison becomes difficult to hold in the mind, which is exactly why geologists use physical measurements instead. The last Yellowstone supereruption, 640,000 years ago, deposited recognizable ash across the entire western half of North America. Cores taken from the seafloor of the Gulf of Mexico, more than 1,500 miles from the eruption site, contain a distinct Yellowstone ash layer from that event. The material traveled that far, fell into the ocean, and settled into sediment that has preserved it for 500,000 years. That is not a future scenario. That is the documented record of what this system has already done. The initial phase of a VEI-8 eruption would produce a column of ash and gas rising 30 to 50 kilometers into the stratosphere within the first hours. At ground level, pyroclastic flows, superheated mixtures of gas, ash, and rock fragments moving at speeds between 100 and 700 kilometers per hour, at temperatures between 200 and 700 degrees Celsius, would cover an area extending hundreds of miles from the term pyroclastic flow appears in every description of major eruptions. But it is worth pausing on the physical reality. This material does not burn what it reaches. It envelops Italiano. Nothing in its path survives. No structure, no shelter, no elevation. The immediate kill zone in the first 24 hours would extend approximately 500 miles from the park boundary. Think about where that place is. Denver sits 550 miles southeast of Yellowstone. Salt Lake City is 290 miles south. Boise is 380 miles west. Within the first day, the question for those cities would not be evacuation logistics. It would be whether evacuation had begun in time before ashfall rendered roads impassable. Volcanic ash, at sufficient depth, collapses roofs. It clogs engines. Mixed with moisture, it forms a compound that blocks drainage systems. Agricultural land under ash coverage becomes temporarily sterile. The deposit from a VEI-8 event would be measurable across most of the continental United States. The immediate destruction is the first chapter, but the most unsettling part is still ahead, because the eruption's effect on the planet does not end when the ash settles. It begins. The mechanism that extends Yellowstone's impact from a regional catastrophe to a global one is not the ash itself. It is what the ash carries into the upper atmosphere, primarily sulfur dioxide, which reacts with water vapor in the stratosphere to form sulfate aerosols. Those aerosols reflect incoming solar radiation back into space. The result is a measurable, sustained reduction in global surface temperatures, operating on a timescale of years, not weeks. The closest modern analog is the 1815 eruption of Mount Tambora. That eruption, AVEI-7, 1/10 the scale of a Yellowstone VEI-8, produced what historians documented as the year without a summer in 1816. Frost occurred in New England in June. Crops failed across Europe and North America. Famine followed across parts of Europe and Asia. An estimated 71,000 people died directly from the eruption. The secondary death toll from starvation and disease in the following 2 years was an order of magnitude larger. Tambora was 1/10 the scale. A Yellowstone VEI-8 event would inject roughly 10 to 100 times more sulfur dioxide into the stratosphere than Climate models project a global temperature reduction of 3 to 10 degrees Celsius, sustained for between 3 and 10 years. At 3 degrees of cooling, global grain harvests are severely compromised. At 5 degrees, sustained agricultural production in the northern hemisphere becomes functionally impossible for the duration. The ice core record shows that every major civilizational disruption in the last 10,000 years, periods of sudden population collapse, mass migration, and political instability across multiple continents simultaneously, carries a corresponding volcanic signature. The scale comparison that makes this concrete. The global food system today operates with roughly 90 days of grain reserves at any given time. A volcanic winter lasting 3 years would exhaust those reserves within the first season. The cascading effects on supply chains, political stability, and the infrastructure systems modern civilization assumes will continue operating have no historical precedent at current population levels. This is not a catastrophe scenario constructed for effect. It is the logical extension of what the geological and historical record already shows happened. The last time a system of this scale erupted, in a world with a fraction of the current population, the question that the previous evidence leaves open is the most important one. How much warning would there be, and would it be enough? The USGS Yellowstone Volcano Observatory monitors the system continuously, using a network of seismometers, GPS stations, stream gauges, and ground deformation sensors. The network is among the most sophisticated volcanic monitoring systems on the planet. What it can detect is well established: earthquake swarms, ground deformation rates, changes in hydrothermal output, variations in gas emissions. What it cannot do is predict the precise timing of an eruption or definitively distinguish elevated activity from a pre-eruptive sequence until the sequence is already underway. The operating distinction here is between detection and response. The United States has no formal evacuation protocol for a Yellowstone supereruption. This is not an oversight. It reflects a genuine assessment that an orderly evacuation of the affected region would require months of lead time and infrastructure capacity that does not exist. Federal emergency planning acknowledges Yellowstone as a Category 5 natural hazard, but does not include a response protocol for a VEI-8 event, because no operationally feasible response protocol for a VEI-8 event exists. What this reveals is a broader truth about the relationship between geological timescales and human institutional planning. The systems we have built, monitoring networks, emergency management structures, international food supply chains, were designed for the hazards of the last 100 years. Yellowstone operates on a timeline measured in hundreds of thousands of years. The gap between those two scales is not a failure of science or policy. It is simply what happens when a civilization very young in geological terms tries to plan around a system very old in every other. What Yellowstone ultimately represents is not a disaster waiting to happen. It is a reminder of what was always here. The park was set aside in 1872 because it contained wonders, geysers, hot springs, wildlife, landscapes that seemed to exist outside the ordinary rules of the natural world. That instinct was correct, though not in the way its founders understood. Yellowstone is exceptional not because it is beautiful, but because it is honest. The heat beneath it has not been concealed. The ground movement is measured and published. The historical eruptions are in the scientific record for anyone who looks. Most geological systems of this scale keep their history hidden in rock sequences that require specialists to read. Yellowstone displays its evidence at the surface, in water that boils without a fire source, and ground that moves beneath your feet. The difficulty is not that the information is unavailable. It is that the timescales involved are simply too large for ordinary human attention to hold. We are very good at preparing for the hazards we have already experienced within living memory. We are much less equipped for the ones that operate on schedules older than our civilization. The ground does not wait for us to be ready. We're one layer deeper than when we started. Subscribe and follow this investigation wherever it leads.